I see my work as kind of like a big long hike with lots of trouble along the way, but the reward is always worth it. It's the investment that gets you far, and then that's not necessarily enjoyable, but the part at the end is exciting. So this project has been a big interdisciplinary effort, so it's trying to connect between some pretty technical math topics, the partial differential equations, and what's going on in fire management on the ground for fire suppression, mostly around the United States. When we get going with it, it's going to be a big model with a lot of switches, and so people will be able to analyze archive data all they want, but we're also hoping to do prediction. So what's going to happen in 2018 this summer? What's going to happen in 2019 going forward? We spent a lot of time with the technical topics, reviewing it around with my committee. So lots of iterative development, getting towards the final answers, making sure our numbers say what we think they say is always exciting. And so we've seen a lot of success there, especially on a simpler version of the models called ordinary differential equations. So start small and go big. Yep.
Okay, hello everyone. My name is Brianna Magwal, and I am in my second year of the Forest Sciences Master's Program. It is my pleasure to introduce to you our next speaker, Alex Masarie. And Alex has been in the Forest Sciences Doctoral Program since 2014 and is advised by Dr. Yu Wei. He also completed his master's program at CSU in 2011, where he focused on single fire suppression and stochastic programming methods. Today, Alex will be discussing his research on identifying suppression risk factors from firefighting data, using a risk data model for resource requests and mobilization data from 2011 to 2016. He will be interpreting what he learned from the coefficients of his model by focusing on a few test cases. Please help me in welcoming Alex Masarie.
Cool, thank you. Cool. All right, really exciting stuff. Thank you, Brianna. Thank you all for being here. It's my pleasure to present. As she was saying, Dr. Wei is my advisor. I'm also advised by Dr. Juliana Oprea out of the math department here at Colorado State. Rounding out my committee are Matt Thompson and Aaron Belval. They're at the Rocky Mountain Research Station in Fort Collins. And then our steering person in Missoula is Dave Calkin. So let's get right into it. I'm going to start this talk with an ecological context and finish with an ecological context. And in the middle, it's going to blow up into data and modeling. So the central tenet here is multi-fire problems will be ours for many fire seasons to come. Right? We're very familiar with what's happening out there. We're also very familiar with our role in this. We have to reduce forest fields, and it's going to be a slow march. We're trying to work smarter, not harder. A big example of this is species restoration. We come to learn these things. This is the red cockaded woodpecker in Florida. I recently learned about it, but it's a fire-dependent species, and folks in Florida are returning fire every 2 years to this little bird's habitat to make sure it gets what it needs. So this is kind of a marginal management strategy. I'm going to say that margins matter on the human side of this problem too. So we're going to be looking at fire suppression, the big equipment that rolls out, and what that data looks like. So what I mean by fire suppression, here's the classical kind of picture. You have time series, so you're looking at kind of 2012, August 5th through August 31st. The vertical axis there is fire growth. This is a Berry Point fire. It was burning in Oregon near a small town of Lakeview. The fire itself is in the gray, the light gray. It's kind of expanding, and then the dark gray is the part of the fire that we've contained. Right, so maybe that's digging line around it, maybe it's dropping the proper amount of air tanker, slurry around it, and eventually we contain that fire, it reaches its final size, and we all go home. This process involves allocation, so I'm going to use that buzzword a lot, where out come the resources. Here's firefighters in the bars now, overlaid on top of the fire, and hand crews, represented by the Pulaski there. They're mobilizing as the fire grows to work, and then as the fire gets contained, we need fewer and fewer until out it goes. So what is more, during the Berry Point fire, there was actually 2 other fires simultaneously growing, the Holloway fire and the Rush fire. I'll talk more about them, but this work looks at the time series aspect really closely. Okay, we look for areas where those 2 fires had big mobilizations, and then the Rush fire was just getting started. So this is the fundamental research question for our group, at least, is how can we most efficiently use our stuff when we're not quite sure what's going to happen in the future? So let's zoom in on 2012. If you remember, this was Hurricane Sandy year. All right, so the big fires of that year are actually the Holloway fire, which we saw and I'll talk about more, and the Rush fire was on the top 4. They were giant fires in California and Nevada, respectively. A lot of mobilization that year. We saw 50 plus Type 1 management teams going out. They sorted themselves all over the country. We'll see more of that later on. Tactical crew mobilizations were a little bit higher than average. 2012 saw engine mobilizations that were a lot higher than average. We spent $1.9 billion. So this model looks at situations like this, where it's 2012, we're trying our best to manage fire, but there's this big kind of super complex, if you will, of fire. Not only was the Holloway fire burning here, it's a complex in itself. These little dots are MODIS fire detections, so the light bulb heat of the fire in megawatts. It was burning across this interagency boundary, causing some complicated paperwork to be filled out. The Rush fire was getting started down in California, and it was just kind of a large conflagration that had a big impact on the nation. So what does policy say? What do we do when these things pop up? Is it implementable? Who's in charge? So I'm just going to read. The National Response Framework provides a comprehensive national all-hazard approach to domestic incident management across a spectrum of activities, including prevention, protection, mitigation, and recovery. Okay, good, we got it. Okay, this project is a lot about that person that would be the top-level manager, looking at fires on the landscape and trying to be flexible, risk-sensible, and robust. You know, this person is sometimes the fire emperor, but I've heard them called the fire czar, the fire manager. Sometimes that person exists when we're at high alert levels, but sometimes that person is not existing and most local crews are managing themselves. So getting into the data review, I have to start talking about categorical decision support because it's so common. It's Smokey's arm, you know. So we don't use Smokey's arm, we use the preparedness level. You can get this on your Facebook feed or wherever you like. And there's policies associated with these 1, 2, 3, 4, 5 alerts. For number 3, for example, it's very specific. 2 or more geographic areas have major commitment. Maybe NIC, the National Interagency Collaboration or Coordination Center, is running the show a little bit. Type 1 teams are out, and crew commitment is 50%. So these are metrics that really matter. So that's kind of where I started. Now you're looking at a time series through the year of 2015. Okay, all I did was add the categories together in the vertical axis. So when you see up here, it's getting up towards 30. I'm adding up a lot of like 3, 4s, and 5s in that situation. Across the nation, this is a lot of fire activity. And of course, the archive extends. You know, we have this data for 2011 now through 2016. And the preparedness level represented a big kind of test case division for us. So we look on the one hand at PL45, where workloads are thought to be really high. Resources are starting to get scarce maybe, hard to get what you need. And then a normal workload where it's business still, tough work, hard fires to work on and suppress and manage. But maybe it's a little calmer around the rest of the country, for example. So in this project, you're going to see a lot of national time series GIS data. So I put maps and time series. Now you're looking at that preparedness level painted onto the geographic region. And it's July 26, 2014, then the 27th, then the 28th. So you can see, you know, not much is happening. And the big question is, could we have predicted this change? And on the 29th of July, you'll notice there was an elevation from preparedness level 2 to preparedness level 3 in Southern California, okay, and a de-escalation in the Eastern Great Basin there from 4 down to 3, right? So the motivation of this slide is, you know, why might a more complicated model be favorable just trying to predict these numbers? Well, because we know there's a lot of processes going on behind the scenes. Here's a little data animation I like to kind of use to talk about it, where this is coming from a database that's available online for all of you to explore too. But it's the energy release component of fuels. The country is kind of drying up seasonally, and these flashbangs of fire activity are happening. This would be confounding information to the preparedness level prediction we need to incorporate and somehow do something with. So our model looks at this black box concept. When we're measuring people's risk preferences, why does PL bounce around? Why do people make decisions they do? We have data on both sides of the problem. We have risk data, lots of it, and we have demand and supply. Like, where were people going? What were allocations levels? We've seen that for the 3-fire super complex already. Work being done on this is just to ask folks, okay, what do you think? Here's a scenario, what would you allocate? Or here's a list of resources, what do you think is scarce, and when does it become problematic in your management? So we've read these and worked through them. Our approach is kind of the same. We look in the black box and we propose a big math model inside. Okay, and instead of interviewing the people, we come up with a strategy to interview their actions, so to speak. When people made decisions and mobilized resources from point A to point B, which direction did they go? What did they leave behind? What were they going towards? And, it's a data process. So you're going to continue to see GIS data. We have a demand potential that's out there. What do people want and where is not always certain. So we need to do something to model that. And it's a directional process as you decide north, south, east, west, where to go. So our black box concept is definitely risk preferences, but we're more interested in expressed risk, right? What did people do instead of how were they thinking at the time? So when you start in some of these awesome papers, here's one from Klein in 2010. It's talking about what is important is that these dimensions reflected different classes of causal factors that were being learned and interpreted by managers to suggest and constrain courses of action. Well, what were the managers looking at? Maps, maybe. Okay, they were certainly fundamentally worried about safety. The WUI, here's our nighttime illuminance layer from GIS. They're certainly worried about how long it's going to take to get my resources to my fire or from their current position. And then a whole number of other factors might appear on their desktops. This could be computerized fire spread behavior software, or it could just be a map that they have on their actual physical desktop. To feature some of them that we're looking at, the first one is that radiative power in megawatts of the satellite detection. And we've smoothed it over the surface of the US to kind of get this aggregate how hot are fires around the country layer. You've seen that flashy picture of energy release component. It definitely goes into this, how dry are fuels. We're also using the burn index now. The burning index is a little more rapid update, day to day, week to week. ERC is more seasonal. And then we have some information about fire cost. It's a little bit sparse there. We take the staffing categories, preparedness levels 1 through 5. A big database for us is that fire occurrence database. It's available online. It's an amazing spot to go do fire research. And another one that's interesting for this model is a data that's just uncorrelated spatial temporal noise. In some core aspect of this, decision makers might just not line up with each other just because. Just because it's John and Sally, just because they are who they are. And we're not going to be able to detect that through their data. So that's a lot about risk. Let's look about demand, okay? When people are responding. So this is a new type of plot. We're looking at firefighter type 1s allocated to fires. These are individuals versus the number of engines assigned on fires. This is around the country. The color bar is marching you from May 2012 into October. And you'll see some key features are a start and a finish of low allocation, right? These are the start of the season, the end of the season. Fire never truly goes out in the United States, but there's this calm time in winter. And then what else are you seeing? You're seeing that mid-August maximum out there. Let's see if we're going to point to it for you. Up here. Okay, that was the maximum allocation. That 1,600 engine number was reached right at that point. And crews were also mobilizing so that about 1,500 fire personnel were active, working. And what is more, you see all these loops, right? What is happening? When is it good to allocate more engines than crews? When is it better to allocate more crews than engines? All kinds of interesting dynamics. So now what I'm going to do is add the fire ignitions to this plot. Okay, so on the bottom, you're looking still that start-finish spread of the season and close of the season. But now extending above in the plane are the counts of ignitions from that lovely fire occurrence database. Okay, you'll notice the most ignitions were coming in early July. Our biggest allocations were in mid-August, say. You know, that makes sense, right? That fires have to ignite and spread and start to get big. But again, the dynamics are crazy. You know, this line is tracking all over the place. Here's an interesting spot where, you know, it looped back on each other. What was happening there? Who was mobilizing? Who was demobilizing? So that's what our model gets at. Here we go. It's the model overview. So we have to assume this person exists, the fire emperor. You know, this is someone who's going to manage the regions, and they're going to look at it in the way my diagram is drawn here. They have each region, and each region has kind of a branch of those black boxes out from under it that say, what are the factors that might matter in this region for fire suppression? Each one of those we kind of GIS out. We assess the demand potential over some time step and on a grid resolution that makes sense for our study. And we're trying to tie this to the suppression resource ordering. Okay, so the overall modeling accomplishment here is we're reconciling spatio-temporal correlation with excruciatingly careful numerics. So how do we get careful? Well, we're very careful in how we mesh up the country. So this big U notation is the union of all the GACs, their geographic area coordination centers, working together to form the country. And you know, this is a Google Earth rendering of the interstate highways that connect them, as well as the delineations of the regions. We make fancy grids for them. These are boundary conforming grids. It's really important to know exactly where that highway enters and exits, right at the edge. And they all twist and map into a computational rectangle. So our big giant model just looks like a bunch of boxes connected with the highways. Okay, so when I look at this, I don't see boxes, I see Hawaii. You know, Southern California, Northern California, you know, so yeah. But just wanted to flash that up there. You'll see some bigger models later. So our first test case is really focused on this three-fire complex that you already know a lot about. Flashing up the map there. So in 2012, in the demand data, we see for every 23 requests that came in, only one of those was unfilled or canceled. Okay, so it can be canceled just by accident, that's fine, or it can be unfilled, and this could be kind of an urgent situation if you ask for something on your fire and you don't get it. Okay, so things are bumping along nicely, but you'll notice in this time series plot, you're now seeing a big kind of shock develop. Okay, so along goes the season through 2012, and all of a sudden these red areas, which are California and these regions shown in the map here, have a ton of requests, right? So they're causing an interregional shock on the rest of the country because they're going to start requesting a bunch of resources all of a sudden and at once. So to try to visualize the broad impact of that type of shock on the system, we use this technique that's called a demand heat map. Okay, the core analogy here is a crime hotspot model. So criminals like to rob people in certain areas, and that will happen for a while, and then that will kind of die down as they look for another area. Okay, so in this analogy, fire is the crime, and we're the police kind of trying to go after it. So this is a dynamic visualization, again, of what's happening for type 1 hand crews there from July 20th, 2012 on through that August month. So let's see what happens as this thing plays and the number of crews that they need goes up and down. So right there, here's August 9th, 10th, 11th, 12th, all through the middle of August. It's just California, 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 maybe Oregon. That region of the country is serving as kind of this attractor, this sink for resources. The math methods love this because it just looks like physics, where they're being attracted right to a spot, and then when they're free, they just kind of disperse to wander off. So in addition to this test case and trying to explain it, you know, it's out there. People are finding, this Magnuson and Taylor article finds that planning for regional variability in fire activity and alignments are really key to efficiency, at least in Canada. You know, that's probably true here too, and it's been talked about. Here's another shock. This one is a regional shock. We know well that in 2015, this orange bar shows engines just all of a sudden being requested en masse in northwestern part of the country. Okay, that was happening because there was a lot of fire in the Northwest. The unfilled to filled ratio went from, you know, that nice 23-to-1 to more of like a 2-to-3 situation. So this was kind of another urgent shock. And so what did we learn from our model about engines in particular? So risk preference underlying this whole system differs by resource. Engines were particularly needed in this spot because they respond near the wildland-urban interface. They're able to get in the roads, they were able to get to the Northwest fires and help out. So when we build one of these systems, we get these coefficients with, you know, a headache-inducing number of indices on them. But we divide them out in just this way to try to detect these patterns. We looked at the firefighting resources, the risk layer they're looking at in particular. From the GIS maps, we're looking at the region they're based in, and we're looking at some sort of lag parameter. So back in time, are people remembering things that have been happening over the last 2 to 3 days, the last 3 weeks maybe? And centered on the Northwest, in this case, of course, what do we find? Yeah, certainly, if you compare engines and dozers, this part of our graph is the wildland-urban interface risk layers. They're kind of convolved with all the other layers in here, but you can see the engine response is a lot larger than the dozers, for instance. So dozers are being sent out in a different way than engines. We kind of knew this, but we're able to detect that in the data almost right away. One thing we were surprised about is these fit coefficients have longer memory than we expected. So what I mean is that a coefficient today about today's fire behavior can be just as significant to the model as one 21 or 14 or 7 days ago. Okay, so puzzle for a little bit about what's going on there. And I want to wrap up those two test cases. So we looked at the fire, we looked at those 3 fires, connected them on the grid. There's a nice picture of what the rush fire was doing, large fire behavior. The activity reports are, you know, extreme winds, and a lot of power lines were threatened in this case. And for large fires and engines, we've dug into the GIS database. This is my risk console. Every time I run a model, this thing comes up. Looking in the Northwest, here's our smoothed out fire heat layer. So a lot of hot fires in this region of what is Oregon and Washington. And sure enough, engines are kind of being tracked there. 10 engines are being ordered in this region. 28 engines are being ordered in here. Maybe there's a confounding factor there, like the burning index. It's getting really dry. We're worried. We're allocating engines there. Current research about engines suppressing large fire is really exciting to read. There's 2 new articles out right now that you can check out. And yeah, engines are a fascinating resource in this whole puzzle. So the test case C now, the last one I'll present, talks about comparing 2 sharing practices. So on the one hand, we have Northern and Southern California. You know, this has been a region for a long time, and they have a lot of patterns, a lot of collaboration that happens. So when we dig into it, here's a picture shown for Type 2 firefighters now. And you see the requesting is coming up in certain hotspots, and maybe it's in response to some sort of broad, there's more fire in the north part of our region than the south, or maybe it's responding to hot, dry conditions in Northern California. That's kind of what we're sorting out. We want to compare that north-south versus our region of the world, for the southern and central Rockies. So we're connecting up to the Rocky Mountain. Colorado's kind of in the heart of this. This also includes up to at least to the southern Idaho border there. And then how are we sharing out with the Southwest? And we see here's Type 1 crews being demanded in that region. And what the large fire is doing is there. A reality of our model, sometimes we don't get any data, right? Sometimes there's no action. So we have ways to deal with this as well. So I'm going to flash through these results pretty quickly. They're small, and it's going to be hard to see. But to compare and contrast, we need like a standardized way to look at the data, right? We're fitting maybe 45 different risk coefficients that, the 2 different regions over all the preparedness levels, and it just gets to be a lot. So this is our mechanism. What you're looking at on the left highlights differences in the significant risk coefficients between the 2 models, and we can dig into them. Our methods are nice because we've used redundancy in the regression, so this is a big regression problem. You end up with a matrix inversion at the end of this thing. And we've used some methods to deal with what becomes a really ill-posed problem. So what that means is a lot of things are collinear. When fire heats up, more fire starts. When the weather conditions dry, both ERC is drying out, as fields are drying, and also the burning index is changing. So all these things are moving together. We're trying to kind of deal with that in our model. We spent a lot of time going around with our group and in my committee trying to figure out, what's this coefficient? What does it mean? How does it behave? Do some tests on that. And of course, my software development looks into all the possible details, and we have a function like this in MATLAB where you're going to put in those matrices to invert, give it some, hopefully you can converge, and we're studying these relative residuals, we're studying how long it took, we're looking at almost every detail we can about these models. Our major finding is that these 2 workload classes are very different, and maybe in surprising ways. When the preparedness level, these alert levels, are really high, okay, the risk models are really complicated. There's a lot of factors. When things start to cool down, in those PL2 and 3s, those lower alerts, things get simpler. People seem to be latching on to a couple of factors and just going with those. Okay, so what we're trying to put this to work doing is making better demand forecasts. How can we get better at predicting what's going to happen, where people are going to come in? And these are some examples of the maps you would put together. So it looks like this, and I wanted to feature this kind of flat behavior. This is really common, and that means that the preparedness level itself is a great fit variable, right? We've talked a lot about how we've sampled on it, but it actually shows really well what's going to happen in the region, and that's good news, because a lot of people can see that. That's, it's on my Facebook feed, for goodness sake. So this is a good thing. Limitations of the model are focused on data, right? Where we can't get data, you can see Alaska. What the heck is it doing down there? Alaska is actually really pesky in this model. We have an incomplete set of data for Alaska, and what is more, it's giant and kind of hard to mesh up and get right. So what do we do with that? Finally, we're learning a lot about the lagged behavior. This has been an interesting feature of this whole project, in that in the Southern California, for example, when you look at the new ignitions today compared with that burning index creeping up on you, you find that response is not necessarily right away. Sometimes folks remember what's happening last week. So this plot is kind of reversed now. We're looking at, we might want to try to predict out here, but we see 1 week, 2 weeks, 3 weeks ago, we've had very interesting trends in more and less demand in this region. So can we leverage these? Can we take some of these points and use it to make a better guess about, what ultimately is a chaotic system of humans? Okay, blasting through the key findings here. We've scaled from incident level to national level and looked where the system is stressed. We found risk response data differ by the region of the country, the firefighting resource type, which makes sense, and this preparedness level category. Good news. Significant coefficients in the expressed risk model for these national fire management problems have more long-term behavior than we thought, which is exciting and surprising. And we've done a lot to enumerate pros and cons of the methodology itself. So to land now in the ecological context, where do humans fit in the ecology of fire? Well, we're kind of like the woodpeckers too. We do it differently. So there's this idea that humans are going to be shepherds to slow fire restoration stewardship, right? And yet fire suppression is not going away, right? You have the scales tipping towards protecting homes and life always, reducing smoke always. Smoke jumpers are just cool. We want to use them. We're going to use them, duh. And then even flow of timber harvest, all these factors add up, and we're not going to stop putting fires out. This is an example of the Gatlinburg fire in Tennessee. You can see in this little photo, most of the community is burned. This resort is unburned, and what does this article say? Well, the CEO came out and said, you can be assured that the resort will be back bigger and more beautiful than ever. So we're not going away from this problem, right? And so that's what we hope to do. We've done a lot of math, we've looked at a lot of models, ran a lot of computer stuff, and we're looking to kind of boost the technology of this situation, to a more calm fire future, which would be nice for all. And I'm going to stop there. This project is based on lots of past research. And then I'll leave some time for questions. I wanted to thank my advisors again. Miriam was in here. She's helped me out a lot. These travel funds have helped me kind of get animated and talk with people I never thought I would talk about or talk with on this project. And yeah, there's the allocation happening in real time, 2012. You figure it out. Thank you. Yeah, maybe a couple of questions or one. Yeah.
The model gets better at predicting, or preempting resources. Is there a recommendation of like the best way to use that information? Would it be like more capacity building regionally, or preemptively like mobilizing?
Yeah, it's an awesome question. One answer might be this concept of STEX, right? Sand tabling exercises. We love to do on single fires. It's actually a sand table, and you sit around and look and game it out and see what happened. What about national level sand tabling exercises? They happen, but it's going to start happening more. And hopefully our model will be like, all right, here's the scenario A, here's the scenario B. What do you do? Anything else? Yep.
I was curious if you looked at all at how property values influence fire resource allocation.
Yeah, I think that's an interesting. We don't have a direct layer of property values in there. You can see how this methodology works. You can just kind of slide in these GIS layers where you like. So if that's a GIS layer you had, we'd put it in. Right now all we have is the nighttime illuminance. Like, where are people? Not maybe how much their houses cost. Yeah, in the back there.
The 1, 2, and 3 week demand cycles showing
Yep.
there. If we correlated that with the 14-day assignment cycle thing, and do you have a recommendation for changing that for more effective resource allocation?
Yeah, there it is. I'm glad you picked up on this. Yeah, the 14-day cycle is no coincidence. If you look at, for example, like the duration of assignments, for folks, a lot of crews especially have short assignments, but that 14-day, a lot of people have 14-day assignments. And so it's actually very useful for prediction, right? If everyone's on the same page, we're going to move every 14 days. Well, we have to get on the same page about how we're going to move. And it's actually already happening. A lot of this stuff already happens. Coordination on those rotations is real. But yeah, we're splitting hairs, literally, trying to do it better. Yeah, Pete.
Yeah, great work. Thanks.
Yeah, my pleasure.
Just a couple of comments.
Yeah, go after it.
A lot of times resources are unable to fill because the training has not been provided to have a sufficient workforce to fill those roles. And so that's another topic for another time.
Yeah.
The other big deal, I would think, is aircraft and air resources.
Yeah.
And you can deal with that at another time.
Yeah.
As far as expense and allocation, that becomes a really big issue, short-term and long-term.
Yeah.
As far as cost and the politics of who's going to be able to negotiate to use those resources.
Yep.
But thanks, this is great.
Yep. Yeah, air tankers, they're wild. I mean, $10,000 per minute. Like what?
We used to do 21 and 30 days.
Yeah.
And now, mainly for safety concerns, it's a 14-day rotation. But the savvy crews will hang and stay around, knowing they'll go out for a couple of days. That was a great thing. Thanks, Ed.
Cool.
Okay, so thank you to our presenters.
Maybe touch base after.
Sorry.
Go ahead.
And thank you everyone for attending today's seminar. Next week we'll be having a couple more grad students from the department present as well. So hope to see you next time. And thank you.
Yeah.